Hello sir, good evening to one and all. Sunday I have arranged one class, so this is highlights of the Sunday's class, and it is also available one of the important question in video question paper as well as BLD Engineering College assignment. This expression consists very important because in general transformer is known as one of the high efficient device, because that's why it is mainly used in different sections of the power transformation from generation to consumer's point, because no such equipment is available for transformer. Hence AC transmission is popular all around the world, because if such competent device is available in DC system also becomes competent. That is the later story. Here the leakage reactance, how it takes the important, some of the useful flux in the machine, some of the not useful flux also developed. So leakage flux creates in the circuit, magnetic circuit. This leakage flux will cause leakage reactance. This leakage reactance generally should be low for good transformer. If leakage reactance is high, then high heating effect is developed and performance of the machine or transformer also reduces. So leakage reactance should be low as such as possible. As the similar case of losses should be low, because practically already we are knowing what is the value of efficiency of transformer, approximately 95 to 98%. Then we can concentrate on such a design which keeps the iron loss to lower value, leakage reactance to a lower value. To derive the such expression, we have to assume some assumptions. So primary and secondary windings have same axial length. Now you see there LC be the height of winding. It is a core type transformer. It consists two windings. One is primary winding, one is secondary winding. BP is the radial width of primary winding. BS is radial width of secondary winding. In between primary and secondary winding, ducts are placing for cooling purpose. Hence its width is small a. The flux distributes along the height of the winding, or flux runs along with the height of wind or parallel to the height of wind. So phi p is the leakage flux. It is links to the primary winding, and phi naught is the duct flux. This duct flux links 50% to primary winding, 50% to secondary winding. If the phi naught is duct flux, phi naught by 2, 50% of phi naught links to the primary, 50% of phi naught links to the secondary. That is the meaning here. Ampere turns of the winding goes on increasing from one end to other end. That is shown below part of diagram. So to make the derivation, some assumptions are required. You remember some 3 to 4 very important. Both windings height remains same. Very easy. Both winding height remains same. LC is the height. Both are equal here. Number 2, flux distributes or runs parallel to the height of winding. That is the very important. then MMF goes on increasing linearly from one end to other end, sir. That is also important. The MMF for the iron parts is negligible. That is also important part. Primary MMF, primary winding MMF must be equal to secondary winding MMF. Primary MMF is IP into TP. Secondary MMF is IS into TS. So you remember sum 5 to 6. You write there before start. Then you have to write all these things also. Details of. You have to write the details of flux also. Phi P is the leakage flux through the primary winding. Phi S is leakage flux through the secondary winding. Phi naught is flux through the duct. L naught is mean circumference of duct. LC is axial length of windings. BP and BS radial width of primary and secondary windings respectively. The leakage flux can be found for two portions. One is main conductor portion, second one is duct portion. So there are no problems actually in this section, only derivation is there as per your syllabus, as per VTU exam. So this stands for very important. If it comes, it may be for 10 marks. Then how many conductors are there? We are having two conductors. One is primary winding conductor, second one is secondary winding conductor. Then consider a infinitesimal strip of width dx, width of dx at a distance x, at a distance x from the primary winding edge. You see the diagram from the primary winding where strip lies. So one end of the primary, the strip lies at the distance of x distance from the one edge of the primary winding. The strip has dx width. So what is the MMF acting across this strip? What is the MMF across this strip? Where this strip lies? Where this strip lies at distance x. What is the total width of primary winding? BP. So x by BP, this is the point where strip lies. Hence this point into IPTP, this gives MMF. Getting the idea? MMF means ampere turns. Ampere turns, IP into TP. But where this lies? At distance x to the total is BP. X by BP. At this point this lies. Getting the idea? Permeance of strip, again standard expression, mu naught LMTP by LC into dx. So these two factors helps to calculate the flux in the strip. So flux in the strip is given by MMF into permeance of the strip. So already I have expressed top, both expressions multiply. We are going to get equation number 1, sir. So equation 1 gives the total flux in the strip. This flux actually links turns, that is called flux linkage. Flux linkage means N phi. N is number of turns, phi is amount of flux linking. So flux linkage in the turns is given by N into phi. Already equation 1 gives flux. So what is the turns it links? Total TP turns. Total TP turns, where it links? By again x by BP. X where the strip lies. Total width of primary winding is PF. BP. Hence x by BP into TP turns. Hence you develop the expression for flux linkage of strip, that is d xi 1. That is d xi 1. So you multiply the equation 1 with this x by BP into TP. Hence we are getting expression in middle. So this is the flux linkage available at that strip. Hence total flux linkage calculation of the primary winding is possible. Total flux linkage of primary winding due to this flux strip, it is possible. So we can take the integration limit. This flux lies at x distance, so it can vary from total width of the primary winding, that is the integration limit 0 to bp. 0 to bp integration limit. Hence it is possible to calculate total flux linkage of primary winding. Make the integration only for x by bp is variable. Make the integration and substitute the value. So xi 1 gives total flux linkage of the primary winding. So mu naught lmtp by lc iptp square bp by 3. Hence we are getting equation 2. Duct portion, similarly we can go for duct portion. MMF is IP into TP. Permeance of duct mu naught into L naught by LC into A. So flux in the strip, we are going to get the equation 3. So one of the assumption that is already knowing, half of the duct flux links to the primary winding and links to the secondary winding, I told earlier. Hence this value gives phi naught. Then this equation number 3 gives phi naught. Similarly we can go for 50%. Flux links with the primary winding 1 by 2 of that equation 3. Hence this flux links entire turns of the primary winding TP. That flux linkage of primary winding due to the duct flux is called xi naught. Xi naught equal to half mu naught L naught divided by LC IP into TP into turns A into TP. We are going to get equation number 4. So total flux linkage of primary winding, it is gives xi 1 total flux linkage of primary winding due to strip flux and due to duct flux xi naught. You can add, then finally I am getting xi p, that is total flux linkage of primary winding. So equation 5 is developed. Hence once you are knowing the total flux, then flux linkage, what is the leakage inductance? That is xi p divided by IP, respective current. Once you are knowing the inductance value, then you go for the leakage reactance. Leakage reactance XL equal to 2 phi FL. You are knowing the inductance value. Above expression gives inductance value. So we may calculate leakage reactance of primary winding, that is 2 phi F times L. You multiply the above expression by 2 phi F, then we are going to get finally equation 5. Similarly, leakage reactance for secondary winding becomes, you should not derive separately, same expression. Now you replace number of turns of primary winding TP by TS, and what is the width of radial width of primary winding? You replace now radial width of secondary. BP is replaced by DS, that is one change. TP is replaced by TS. Rest other terms are same. Now we are knowing the secondary leakage reactance. So I want to calculate total reactance of the transformer. Hence I want to transfer this secondary winding reactance to refer to primary side. I want to convert by taking turns ratio in terms of primary winding with reference of primary. Then XS dash xs dash, multiplying the turns ratio Tp by Ts square, then we are getting the equation number 6. This represents leakage reactance of secondary winding referred to primary side. Now it becomes very easy. Total net reactance of transformer per phase referred to primary side. XP, capital X, means total reactance of the transformer referred to primary side. This equation must be equal to leakage reactance of primary winding plus leakage reactance of secondary winding referred to primary side, XP and XS dash. Then we are getting equation number 7. This is the final expression. Total leakage reactance of transformer referred to primary side. Sir, there are no problems. I have given one of the assignment book, one of the assignment question, practice. If it comes in the examination, it should be minimum 10 marks, 10 to 12 marks, and direct derive the leakage reactance expression of single phase core type transformer. Okay, very interesting. Practice. All of you practice. Thank you, sirs.